Section 3.2, Newton's first law of motion. Sir Isaac Newton is one of the most important physicists in history, and he came up with 3 laws that explain all motion in our universe. We're going to take a look at Newton's first law of motion. It'll begin with Galileo's thought experiment. Galileo Galilei was a physicist who studied physics, and he said that a force is needed to keep an object moving on a level surface because the force of friction opposes motion. And without friction, the object would keep moving forever and ever. An object with constant velocity has a tendency to keep moving at a constant speed in a straight line forever. So take a look at these 3 diagrams. Imagine we have a descending and ascending ramp, kind of like a half pipe for skateboarders or snowboarders. If there is no friction, the ball will continue to move up and down the descending and ascending ramps over and over and return to the same height from which it started because nothing is opposing the motion of this object. There's no friction to slow it down. Once it has that energy, it'll continue forever and ever until it's interrupted by some sort of other force. If you were to take the ascending ramp and start to decline it, the ball would continue down the ramp, but it would try to seek its starting height. If you completely descended the ascending ramp, so it was horizontal, the ball would keep on moving, and it'll keep on moving in that straight line forever and ever because no force is opposing it. Inertia is defined as the property of matter that causes it to resist changes in motion. Inertia is directly proportional to the mass of the object. So I want you to imagine a mouse on a skateboard. I'll do my best, bear with me. And this mouse is on a skateboard. And I want you to imagine the same skateboard, but this time, instead of a mouse, we are going to have, and excuse this drawing, or this irrational example, we have an elephant. On a skateboard. Imagine both of these were coming towards you. Which one would be more difficult to force to come to rest? You can imagine that the elephant, which carries more mass, would be more difficult to stop. Whereas the mouse, because it has less mass, is easier to stop with a force. So the property of matter that causes it to resist change in motion is called inertia. So the mouse has less inertia, and the elephant has greater inertia. Inertia is a property that is directly correlated to mass. So the more mass an object has, the more inertia it has. And the more likely it is to resist changes in motion. In fact, a very common way to express inertia is by saying an object at rest tends to stay at rest and an object in motion tends to stay in motion. And this is because these objects possess inertia. So I want you to think of these 3 examples, and we're going to explain how inertia can describe or explain the sensations that you would feel. Imagine you were sitting in a car, and the car is at rest at a stoplight, and the stoplight goes from red to green. And the person driving the car, instead of gracefully easing on the gas pedal, slams on the gas. If this person rapidly accelerates, the sensation that you will feel is yourself being pushed back into the seat of the car. And the reason why is before that light turned green, you are at rest. And your body, because it has mass, wants to stay at rest. The car is now in motion. And the car is moving forward even though your body wanted to stay at rest where it was. So you're being pushed back into the seat of your car because your body wanted to stay at rest where it was in the position back at the stoplight before it turned green. So we can write a little summary of that. If a car accelerates from rest, objects inside will tend to stay at rest. And the experience or sensation that you feel is that you'll be pushed back into the seat of the car. Let's think about the opposite. Imagine the car was in motion and you suddenly slammed on the brakes. How would the sensation that you experience differ from when you slam on the accelerator? Well, if your car is moving forward and you're inside the car and you're moving forward and you suddenly slam on the brakes, then the car is going to want to come to a rest. But your body that was in motion is going to want to continue in its motion and continue moving forward. That's why we have seatbelts. Seatbelts hold us in our place. Though the car has stopped, our body wants to continue moving forward, and the seatbelt's actually holding us back. In fact, that's why they were invented. Otherwise, every time you slammed on the brakes, you'd be thrown forward, and if this was a rapid deceleration, you could actually fly through the windshield. Next example is a curling stone, and a curling stone is a very heavy object. And these heavy objects tend to stay at rest unless you apply a force on them. They are going nowhere unless you apply a force. I hope that looks like a curling stone and not a hamburger. I don't know if that's helping. So a curling stone at rest stays at rest because it has a lot of mass and therefore a lot of inertia. Next, the trick to getting ketchup out of a bottle. The trick to getting ketchup out of a bottle can be hacked by understanding physics if we know what we're doing. So here we have ketchup in a bottle, and we want it to get out onto our French fries. I hope this looks like ketchup in a bottle and not a murder scene. I'll draw a plate. Now, we can apply the principle of inertia to allow us to figure out how to get this ketchup out of the bottle. So what we're going to do is we're going to send the ketchup bottle and its contents into motion. But we're going to suddenly stop the bottle in its path. So we'll send it rapidly forward, but suddenly stop the bottle. If we suddenly stop the bottle, the ketchup itself will want to continue in its state of motion and it will leave the bottle. Impress your friends. When they are talking about how to get ketchup out of a bottle, or even if they're not talking about it, just bring it up and let them know the physics way to do it. Send the bottle and its contents into motion. Then suddenly stop the bottle and the contents will continue to move out. The contents will leave the bottle. Right. These two situations appear in your textbook. I want you to make a prediction as to what you'll expect and explain them using the laws of inertia. So make sure you fill in these 4 boxes for homework. Okay, so Newton's principle of inertia, Galileo's principle of inertia led to Newton's first law of motion. This is the first of 3 laws that explain how objects move in the universe. And Newton's first law states, if the net external force on an object is 0, then the object will remain at rest or continue to move at a constant velocity. So, if the net force on an object is 0, then the object will remain at rest. This is the first situation. Or continue to move in a constant velocity. There are 2 possibilities for an object's motion when the net force acting on the object is 0. So remember, 2 possibilities when the net force acting on an object is 0. Either it's at rest or moving at a constant velocity. In each of these sample problems, the net force is 0. So what we need to do is to find the unknown forces. For example, in this diagram, in diagram A, we have a force of 12 newtons acting up on the object, another force of 8 newtons acting up on the object, and then we have a force of gravity acting down, and we want to know the magnitude of that force of gravity. So we can actually predict it quite easily in our head if we know that the total of the forces acting in the upward direction is 20. Then the force acting down, the total forces in the downward direction, must also be 20. So the force of gravity should equal 20 newtons down. But let's prove this. We know that the net force is 0. And we know that the net force is equal to 12 newtons up plus 8 newtons up plus the force of gravity in the downward direction. If we solve the force of gravity by itself, we can bring these guys over the equal sign to isolate for the force of gravity. When we do, they change signs, so we have negative 12 newtons up minus 8 newtons up. We can simplify that. Since they're both in the upward direction, we have negative 20 newtons up, which is the same thing as positive 20 newtons down. So we were able to prove what we predicted the force of gravity must be in order for the net force to be 0. Okay, let's try sample problem B. In sample problem B, we know that the net force is 0, so everything must balance each other out and cancel each other out. So what's happening in the upward direction must equal what's happening in the downward direction. So if there's one force down and it's 22 newtons, then the normal force in this example must be 22 newtons up. If the total of the forces in the right direction is 28, then the total in the left must be 28. So if we know that one of these forces is 15, we know that 15 plus 13 is 28. So we know that this unknown force is 13 newtons. Okay. I want you to use your textbook to explain how a modern seatbelt works using Newton's first law, and give an example of 2 other devices that rely on Newton's first law and explain how they work. There are homework questions at the bottom that you need to try, and do any LMS quizzes corresponding to this section as well. Good luck.